welcome. Thank you very much for coming. Is that the timer? Great. The timer is even running. Yes, so today I'd like to talk to you about Anoma, one architecture for full stack decentralization. And I'd like to start with a brief historic recap of where we started and how we got to where we are today. And so I would consider, we started with the first evolution of protocols, which was scriptable settlement. And this started with Bitcoin, and there was a long tail of Bitcoin-like forks, whether this was Litecoin or even something like Zcash. It's always in the scriptable settlement model. And people try to build applications on scriptable settlement. They try to build things like colored coins or Namecoin or even the global Bitcoin stock exchange. Who here in the room has ever used the global Bitcoin stock exchange? Okay, never mind. It was a completely unregistered securities exchange back in the early days of Bitcoin. It was interesting. But the important thing to remember is that a lot of these applications work, but they were incredibly clunky. And sort of, for example, for Namecoin, you needed to run a forked Bitcoin client in order to make this work in practice. Then with Ethereum in 2015, we went to generation 2. We went towards programmable settlement. And all of a sudden, instead of having colored coins, we got ERC20s. Instead of having Namecoin, we got ENS. But we also got a ton more things that no one really thought about when Ethereum was being developed, like DAOs, like NFTs, like soul-bound tokens. So we got a lot of novel applications that no one really imagined building when we were still in the scriptable settlement model. And so nowadays you can build things like DEXs, AMMs, NFT marketplaces. But again, they work, but they're clunky for different reasons. They're very composable at the settlement layer. But they, generally speaking, have at least one centralized Web 2 component right now as well. Because what is the general pattern? And is this a pointer? Oh, you see this on the slide on the bottom. What's the current design pattern for modern dApps? It's a user doesn't have a transaction. Users have messages. Users have intents. Users have partial state transitions. And they sign these things, and then they send them to a central server, right? This is how OpenSea works right now. A user doesn't submit a transaction directly to Ethereum. No, they sign a specific message, send it to the central OpenSea server that then aggregates a bunch of these messages, does some compute, and then ends up settling this on-chain. And this is a pattern that you see over and over again, whether this is for OpenSea or for Optimism, or for any rollup, or even for like things like Gitcoin. It's always this pattern where people don't have transactions that are directly executable on-chain. They rather have intents that need some amount of counterparty discovery to make work. So I'd like to also talk, of course, about sort of programmable settlement plus, everything that has happened since 2015. But to me, this is still very much the same architecture. This is still very much the same generation of programmable settlement. Like, yes, we had a bunch of advances from proof of work to proof of stake. Like Cosmos led the way there with Cosmos proof of stake, right? We had advances in scaling. We had advances in privacy. We had advances in consensus, actually, with regards to tenement consensus, for example. But it's still fundamentally the same model. It's just programmable settlement. It's what the Ethereum trialed and sort of got to market in 2015 in a slightly different color and a slightly different flavor. But it's fundamentally the same thing. But the really important insight here is that settlement is not sufficient. Settlement is sufficient if parties already know who they are and what they want. So like, settlement is only sufficient if you want to do a simple transfer. Like if I want to send 10 USDC to someone else, then settlement is sufficient. But for anything more complex, you need something more than settlement. When you actually look at most applications need counterparty discovery. They need to help people to discover others with whom they can settle. Good examples here are DEXs and marketplaces, right? Like in a DEX or a marketplace, I don't have a fully fledged transaction. I have a partial thing. Like I have the intent that I have currently some ETH and I would like to hold a CryptoKitty. Or maybe I have the inverse, that I hold a CryptoKitty and would like some ETH in exchange for this. But this is not something that I can execute on chain. You have the same thing with quadratic public goods funding, where you have project donors and funders. You have even the same thing with DAOs and optimistic and ZK rollups. And I'll sort of go more in depth on how these applications actually look like right now. So let's switch to what are the current approaches to counterparty discovery. And really there are three general approaches to this. Number one is you do it on the blockchain. This is sort of what Uniswap, what Osmosis does. You just dump it. You do the counterparty discovery in consensus. AMMs are the most gas-efficient way to do this, but when you really think about this, this is kind of silly and really expensive because you're paying to establish a global total order over every single trade, even though there's absolutely no reason to establish a total global order for all these trades. But this is at least very decentralized. Then you have sort of option two, you dump it all, you centralize the entire thing, right? How do you fix a problem? You just build a new centralized component and you call it a single operator database. This is what OpenSea does, this is what 0x does, this is what Flashbots does, this is what rollup sequencers do, what rollup provers do. The problem here is this always becomes a main trusted party. And we've gotten pretty good at least trying to prevent these trusted parties from being able to steal funds. But at the very least, they can indefinitely censor you. And again, why are we building decentralized technology if the major component that makes these applications work end up being a single operator database run by a private company in New York in the case of OpenSea? And then you sort of have the third approach, an app-specific sovereign chain. And DYDX is trying this right now, but the problem is this kind of comes back to point one, which is now we just dump everything in consensus. And yes, if you do this as an app-specific sovereign chain, you can hide over this fact because you aren't competing for execution time or for gas with other applications, but eventually also reaching like fundamental scaling limits by dumping everything in consensus. The other really important point to note here is that programmable settlement gave us composability at the settlement layer, right? Like a contract can call another contract. But in the current model where we have intents, we're losing this composability, and we're also losing this composability in the third model, because fundamentally I can't build a new application that reasons through the intents that get sent to the OpenSea server or the intents that get sent to the Optimism rollup. Yeah, so I think really the single biggest trade-off is that we lose a lot of composability at the application layer if we always think about this model as transaction-centric. So, with this sort of brief introduction, I'd like to briefly talk about Anoma and what I'd consider the third generation of protocols, an architecture for full-stack decentralized applications. And so I'll give you the entire tagline, which is, Anoma is an intent-centric, privacy-preserving protocol for decentralized counterparty discovery, distributed solving, and atomic multi-chain settlement. And I'll go into some of these components a little bit later throughout this talk, but this is sort of the high-level tagline. Fundamentally, Anoma is intent-centric. Users, generally speaking, don't have transactions. Users have intents, they have partial state transitions, they have partial transactions. They don't have something that's settleable on-chain. They have something that needs some sort of counterparty discovery mechanism in order to become settleable in the future. The architecture also provides composable privacy, because I think this is another important thing, that not everything should be public, but also not everything needs to be fully private. There is a very big difference between sort of transparent, shielded, as well as private state. And application developers need to be able to choose whatever they think is the right model. And by the way, here the difference between shielded and private is whether you have shared private state or not. So shielded state is about single private state, and private state is about shared private state. Yeah, you have an architecture that provides decentralized counterparty discovery, distributed solving, as well as multi-chain atomic settlement. And if anyone here knows about Tendermint, you'll really like the stuff about multi-chain atomic settlement. So it's a radically new design where intents are binding programmatic commitments to preferences. Rather than expressing and signing over a specific execution trace, which is what happens in all the current virtual machines, right? Like when I sign over a transaction in, let's say, the Ethereum model in the EVM, I sign over a specific execution trace worth of opcodes, where every opcode can sort of arbitrarily change my state. So I have to audit and understand what every opcode in this execution trace does. But with an intent-centric design, users sign over future states that they're willing to accept. For example, a user may hold a Bitcoin right now, and they sign over the fact that in the future they're fine to hold 0 Bitcoin if and only if they hold 100 ETH, right? So users express future states that they're willing to accept. This leads to a ton of advantages. For one, all of these intents are now composable, because I can take an intent that goes from state A to B, for example, and someone else sends me an intent that goes from state B to C, and I can generate a new intent that goes from A to C, because all of these are just like, you net out the state changes effectively. This is also how you can build on-demand rollups with this kind of architecture. And this is necessary for decentralized counterparty discovery, and leads to an interesting paradigm that we call declarative paradigms, which I think is much closer to how actual users think about their interactions with decentralized systems, right? Like when my parents sign a transaction, they don't think that they're authorizing this specific execution trace within a specific VM. They think about the fact that they're authorizing that their state changes, right? Like they are fine with holding maybe one less ETH if they're buying something in exchange. They're not thinking, am I okay with all these contracts being called in the middle? Yeah, and this means that you can design very nice declarative black box architectures where users don't have to care about the thing that happens in the middle, because users only sign intents of what future state changes they're willing to accept, and then the underlying system can figure out exactly how to satisfy those intents and those state changes. And maybe this means that if I want to trade 1 Bitcoin against 100 ETH, there could be 1 counterparty, there could be 100 counterparties. I as a user don't care, because it doesn't matter to me. I just care that my state preference that I signed over my intent is adhered to in the future. So in the future, I just have to check whether my state was updated correctly. So a little bit of what's in the black box, because this black box matters. I won't go through the entire thing in depth, but sort of on the left, you see we start with counterparty discovery. And here we really have intents, intent gossip nodes, solvers, as well as zero-knowledge proofs, recursive proofs, and eventually fully homomorphic encryptions. So users can either author transparent, shielded, or private intents. Some of these will involve multiple zero-knowledge proofs. Some of them will involve somewhat advanced ciphertext. They then submit these intents to an intent gossip network, where that can contain 100 million of these intents, because they're not consensus critical. We can have sort of infinite amounts of them. And then solvers can look at the soup of intents and see which ones are composable, right? Because maybe I have BTC against ETH, someone else has ETH against Atom, and someone else has Atom against BTC. These 3 intents live by themselves in the intent gossip network, and a solver can look at this and go, oh, I can take these 3 things and submit them as a settleable transaction on-chain. Here, the nice thing is solvers use the protocol that we developed called Fervio for front-running protection, where solvers, where any transaction is encrypted against a shared public key of the validator set, which means that the transaction mempool actually only sees encrypted byte strings. And then in Tendermint, the validators only put encrypted byte strings into blocks and finalize those blocks, and in block n+1, the validator jointly decrypts those transactions. But no individual validator or no individual observer can actually try and front-run these transactions, because by the time they're finalized, their ordering is fully established and you can't front, bank run, or sandwich them anymore. Yeah, so now we have the validators and we get to the finalized block. Here this comes now to the execution verification and our unified execution environment, which is called Tiger, which can handle transparent shield as well as private state. Here, one of the nice things, once you think more about intents and less about transactions, you can also parallelize a bunch of the execution at the settlement layer, because intents or transactions with intents that touch different parts of the state can be applied in parallel, because we know they're not conflicting. Oh, I have 6 minutes. Okay. One of the important things to remember is that Anoma is an architecture. Anoma can be deployed in many different ways. Anoma can be deployed as a global L1, can be deployed as a L1.5 to decentralize a specific application that needs decentralized counterparty discovery and distributed solving, or can even be deployed as an L2. Remember, this is fundamentally about giving users the choice in what security model they want to accept. This is, I think, very much comes from this interchain thesis that like different people can pick different security models. We probably want to have homogeneous architectures, but we want to have heterogeneous security models. Right, here are some novel primitives that dApps get. So intents effectively lend themselves towards can be seen as incentivized data availability. You also get programmable threshold decryption via Fervio at the application layer. So applications can define what kind of a batch they want to have encrypted and at what point that gets decrypted. Okay, I will skip over this for the sake of time. I think one of the important things to remember is that when Ethereum came out in 2015, we really couldn't imagine all the applications that it would enable. And I think this is also the same with an architecture like Anoma, because I fundamentally believe that there will be many Anoma-like architectures in the future that will be deployed, in the same sense that there were many programmable settlement architectures being deployed since 2015. Right, so what kind of contemporary applications could we be building? You can be building Xerox, CowSwap, Uniswap, so any of the decentralized exchanges and marketplaces. You can build full stack decentralized rollups, or you can build decentralized public goods funding. Yeah. But, and I won't go through all of these in depth, I'll pick out two, which are novel things that you can't build anywhere else. You can build runtime rollups, because effectively intents are just rollups by default, because as I said, if I have an intent from A to B and someone else has an intent from B to C, a third person can just roll this up into an intent from A to C. And you can also build private auctions, so sealed price, second price auction, sealed bid, second price auctions, where the bids are all kept private using fair value for threshold decryption, and then are decrypted once all the bids are in and the bidding period is over. Yes, coming to homogeneous architecture, heterogeneous security. Protocols can generally be benevolent monopolies. For example, we all benefit from just agreeing on IBC. There is no extra value capture that IBC as a protocol can sort of take on. We all just agree that we all have the same interoperability standards so we can talk to each other. Security domains, on the other hand, shouldn't be monopolies, because they're non-local, they can extract rent, they can confiscate assets, and different people have different preferences, right? I think my parents will have a preference that to them, the best security model is that their local village secures their financial system. To some people in Africa, maybe they care that like they are in global ETH2 security. Like we don't know. And we should give users the choice to pick the security models that they care about, but give them the same underlying architectures so that they don't have to reason through a new architecture all the time. This leads to very nice privacy preserving and censorship resistance from the bottom up. Right, fractal scaling. One of the super nice features, if we agree on the same protocols, is that things like our phones work everywhere, right? Like, I bought a phone in Switzerland and my phone works here as well. This is a very convenient feature of the fact that everyone agrees on the same standard for the cellular backbone. And this really should be the same for applications in the blockchain space as well, where I may want to roam between something like osmosis and secret with the same application, because I now roam across different security domains, but my application fundamentally still works in the same way. And now I'd like to take the last couple of minutes to talk about Typhon, which, if you're aware of Tendermint, is it's a new way to think about consensus. So it's a combination of heterogeneous narwhal and heterogeneous Paxos. And fundamentally what it gives you is the ability to have on-demand sharding. So if you have two blockchains that use Typhon, if there's a large enough overlap in the validator set, those two blockchains can decide to commit to an atomic block in between. So what's the use case here? The use case is, let's say you're the London Stock Exchange and the New York Stock Exchange, and you want to clear, I don't know, $100 million trade between these two block exchanges, right? You want to make this atomic. And so if you use something like Typhon, you can then, most of the time, these chains run by themselves, but when you want to have an atomic transaction across both, you can create an on-demand virtual shard, or we call them chimera chains, to be this atomic thing that's atomic across both chains. This also helps in the more practical example of, let's say, I want to book a flight, a hotel, and a concert ticket, but they all live on 3 different blockchains. Using Typhon, I can have atomic commits across these 3 different blockchains, so that I get my concert ticket only if and only I also get my flight and my hotel. There's talks and specs you can find online. Yeah, I think this really leads me to this, which is that we want to have homogeneous architectures and heterogeneous security models, so that like that, for example, the Swiss central bank can deploy its own blockchain secured by its own consensus to issue a digital CHF. But we want to have the capability to move those assets using IBC into a global settlement layer. Yeah, so Anoma is not only built by me, Awa, and Chris. It's built by a relatively large team right now at Heliax. If you want to find out more, feel free to come find us and talk to us more. Thank you very much. This is Anoma, one architecture for full stack decentralization.